Well, it kind of started by accident, actually. I was doing a PhD in the University of Limerick. So my focus on my PhD was to look at a means of predicting composition of biomass using infrared spectroscopy. The idea was we would patent those models that we developed within the project. I found out it's very difficult to patent an algorithm. And so we changed the deliverable to a business plan for a theoretical company to spin out from that project. And after writing the business plan, I thought maybe, what the heck, I'll give it a go and see if it works. And sort of it just spiraled from that, basically.
In EnXylaScope, we focus a lot on polymers that are coming from wood and straw, and our key polymer is the xylan. And we take the xylan first approach because we think it is the most, let's say, underrated and underutilized polymer. And using enzymes to modify this xylan is the next step of innovation. And we have partners that have discovered some very good novel enzymes that can act on xylan specifically, from which we can make a variety of products. When we take wheat straw, in its raw form, it has a lot of extractives that are not structural in nature. Also, there is another structural element called lignin. As the plant grows, it becomes strong because of this component called lignin. For a plant, it's beneficial, but for bioprocess, it's normally a bottleneck to access the other polymers. So in the first step, we get the extractives out and we can also get the lignin out. But we do it under a very mild process. We don't use pressures, high temperatures. So you get that lignin and all the extractives out, and then the residues from there also goes through the next very mild treatment, where that's where we get the xylan out. And the xylan, it comes as this brown thick soup. And this soup is transformed into a product just by some pH adjustments, neutralization and precipitation. These are also very simple steps. Once we get the xylan out, the solids that are left is cellulose rich. Cellulose can be then converted to sugars, and these sugars can be used for biofuels, some fungal systems you can use to produce oil. So there is no waste left at the end. And interestingly, in the first process, when we remove the extractives and lignin, we also have a process where we precipitate that, and our partner company in EnXylaScope is testing it for packaging applications. And the only solvent we use in this process is ethanol, and we recycle it.
So the worst day is when you wake up and the equipment decide not to work and you have to troubleshoot generally. Sometimes they have a temperament. The good thing that comes out of that is you then get to learn a lot as far as the operation of the particular equipment is concerned. On a good day, I'm always happy if everything goes on well. When we have good xylan that looks very beautiful, we are happy. Everyone is happy here. We have worked over the years through several iterations to improve the simplicity of the process and also cut down on any form of inefficiencies and wastage. Considering the xylan industry is new and emerging, there's still a few uncertainties as far as the economics is concerned. But when we look at the value chain, one of the bottlenecks is the cost of feedstock or the availability of feedstock. One good thing about our process is the normalization of the process, so we can diversify the feedstock stream as well. So the product itself has high value applications, so there is a good potential for economic feasibility.
So one of the benefits of using these residues for enzymatic hydrolysis to ferment the sugars is it's quite a cost-effective process. It's quite fast as well. In a matter of few days, we can get high enough titers to concentrate to have good sugar for a wide range of applications like stock. And the process prevents inhibition, so it's quite robust in these ways. And then the sugar quality is really good, as we can test in the lab for fermentation to alcohols or organics.
At the beginning of EnXylaScope, we started looking for different fungi and bacteria that can break down the the xylans. As an additional product, we also discover other properties. This one is producing a pigment called melanin, and it has a variety of industrial applications. In this plate, if you can see, this too has zones around it, like the empty places, because these two bacteria are stopping the fungi from growing around them. So it can be used for protecting plants from fungal infections. In a lot of companies, if we look at the traditional bioethanol facilities, the pretreatment step gets the xylan fraction out. It's costly, energy consuming step, yet no product comes out of it. So the beauty is we can actually kind of plug this process in any ethanol production facility, get the xylans out, and the residues go for production of sugars and ethanol. It can also be plug and play for paper industries, because paper industry wants cellulose, and their existing process uses heavy chemicals and temperature and treatment. In our process, it's quite mild and they're getting a value from it. So this is a technology that can stand on its own because of the economic potential, but can also be a plug and play system to other technologies that mainly uses the cellulose residue. So if you give us straw, you give us wood, you give us any feedstock that contains xylan, it goes through the same unit operations, it goes through the same processes. It's a complete zero waste process, and every fraction is used not just for its fullest advantage, but for the best value as well.
So yeah, we're extremely active in many areas of the bioeconomy. We cover all different aspects of biomass valorization, both in the analytical sector, but also in the bioprocess development sector. So we work with startups, research institutions, multinationals, catering for their needs in terms of optimizing biomass, their use of biomass, and the technologies for getting value from biomass and waste materials. We're very pleased with the work we've done so far and the progress we've made.